So we're going to work through 7.7 now, volumes of solids with known cross-sections. I really like how this guy went through all of this work to cut up little pieces of squares, because the visual is very, very helpful. So basically what it boils down to is we can estimate volumes as if we knew the size of each cross-section. So basically what it boils down to is we can have squares, we have right triangles, and we can look at more when we get on the next page, and you might be looking at it right now. And what it is instead of, I guess it's right here too, instead of finding, I guess, a line in here and revolving around a line, you can estimate between finding the area between each curve. And instead of making perfect circles, we can make squares or triangles or semicircles. And each side length is based on that, and they call them cross sections, but based off of the difference between each height. So basically what it boils down to, and I like how he even showed you, that for each side length for the square, it's the upper function, in this case he writes f of x, minus the lower function, and again he writes g of x. And because it's a square, every side length is the same, f of x minus g of x. So what does that mean for the area of one individual square? What that means is it's f of x minus g of x, again area, length times width, or squared. And so what that means for us is if we added up all of those, then we would write it as an integral from a to b of the upper function minus the lower function squared in terms of x. Now notice that this is in terms of x, because what's happening is the cross sections are perpendicular, and I like how he wrote it. These cross sections are perpendicular, I'm connecting to that one, to the x-axis. So you'll see that in the directions as well. So let me jot that down. Perpendicular to the x-axis. So what would be the difference if it was perpendicular to the y-axis? Well, everything would be in terms of y. So I still don't know the upper and lower bound, a to b, but these would be in terms of y instead of in terms of x. So like x equals a, x equals b. Up here, this would be like y equals a, y equals b. And then you would just have everything in terms of y, f of y minus, g of y. Squared dy. And it's very similar to the way we did the disk or washer method. So as we look at this other one, so notice that the directions are isosceles right triangles. Well, if they're isosceles right triangles, what that means is that the base and the height are equal to each other. Well, what's the area of one triangle? It's 1/2 base times height. Well, since the base and the height are equal to each other, we can just say f of x minus g of x squared. Now, as far as an integral goes, the only thing that's different, just like when we did revolving around the axis, the pi went in front. Well, in this case, 1/2 goes in front. The integral from a to b of f of x minus g of x squared dx. And that's for perpendicular to the x-axis. So if it was perpendicular to the y-axis, it would be something similar to this. Now, I think you guys know me by now, is if I can figure something out without memorizing it, then I will. And that's what I'm going to show you on the next one, is if I'm told that we have equilateral triangles, and again, notice that these are equilateral triangles made with the x-axis, is if I can figure out what the area is, then I will do that on the test. I will not memorize this stuff. You might be in that camp where you want to memorize the day before, just in case this problem comes up. But it's not even a guarantee that it will show up, and you have so much more to memorize that you might want to do that. So what I do is I actually methodically figure out, well, if it's an equilateral triangle where the length of the base is equal to the upper function minus the lower function, then what I can do is I can figure out what the height is of that. So again, an equilateral triangle has angles that are 60 degrees. So I methodically think about how we have a 30, 60, 90 triangle inside of this. And this piece right here is the short leg, and it's 1/2 of that f of x minus g of x. And I hope you remember from Algebra 2, even in pre-calc, that the long leg, the height in this triangle, is the short leg times √3. So all I did is I took the short leg, which is 1/2 f of x minus g of x, times the √3, so it's √3/2 f of x minus g of x. So then as you think about, well, what's the area of a triangle, it's still 1/2 times the base times the height, and so you can memorize that if you have equilateral triangles for your cross sections, excuse me, 1/2 times √3/2 would be √3/4, and f of x minus g of x times itself would be f of x minus g of x squared. And so what's the area of all of them if we added all of them together? We can move that constant in front, the integral from a to b, f of x minus g of x squared. And again, this is perpendicular to the x-axis. So if they had perpendicular to the y-axis, you just make sure everything's in terms of y. And then on this last one, sometimes I disagree with the author of this stuff because I get different answers depending on what I do. Is if they say the diameter is a semicircle, which I feel like his work does not always say the diameter is a semicircle, although on an AP test it will say the diameter is a semicircle. So what I think about, so it's a great visual what he has, and I really, really like the visual, is think about, okay, well, what's the area of a circle? Well, area of a circle is pi r squared, and the only thing is it's a semicircle, so it's 1/2 pi r squared. Well, what's the radius then? Well, the radius is 1/2 of f of x minus g of x. Well, let me put a 1/2 in front. So if you go through that formula, we're looking at 1/2 pi, and the radius is 1/2. Oh, I don't know why I'm doing it this way. F of x minus g of x. I don't typically put brackets inside of brackets, but I am here. Squared. So what's important is that you realize that not only is the f of x minus g of x squared, but so is the 1/2. 1/2 squared is 1/4 times this 1/2 would be 1/8 pi times f of x minus g of x squared. And again, this is perpendicular to the x-axis. Pretty clear, I think. So what's our answer for the sum of all of them? And by the way, 1/8 times pi is pi divided by 8, same thing. Integral from a to b of the f of x minus g of x squared. And I know lots of people will just memorize these formulas. I like to work it out though. But what you should notice about all of these formulas, integral defined functions for volumes of solids, no matter what, is we have that form that has f of x minus g of x being squared. Okay, that happens no matter what. You just have to, I guess, go back and think about, well, what happens to that constant? I don't like that, purple on purple. You know, and do you just want to memorize these constants? I guess you could. You know, there's nothing wrong with it. There's a 1 in front if you wanted to think of it that way. But now we should be ready to answer a few questions. Yeah, so when you look at this, we've seen a problem like this before. Pretty clear that where points of intersection are 0 and 2. Notice the directions say perpendicular to the x-axis. I just don't like how on part B he doesn't mention the cross sections are semicircles, you know, where the diameter are semicircles. Again, directions on an AP test will clearly state that, whereas this one, it looks like, you know, he just assumes that you understand. But what this boils down to, if we're doing equilateral triangles, then it's going to be √3/4 integral from A to B. Well, we don't need A and B anymore because we know that they intersect at 0 and 2. And then the upper function is sine of pi x. And the lower function is the x cubed minus 4x. But we have to subtract, so make sure you distribute that minus in there. That quantity squared dx. And really all of this work is going to be the same. That was equilateral. Over here is isosceles, which was 1/2. Everything else is the same. Squares was just, that might actually be the smart one to do that one first. And then the semicircles, we had pi/8. And yeah, from here it might just be to your benefit to go straight to your calculator. And we've already practiced how to type that in. Otherwise, I can just jump to the answer key. And by the way, he works through the same way I do, so you'll get the same answer. Note he also shows you how to type into your calculator, so please write down if you have any questions and bring questions to class, but round to 3 decimal places. And notice that the area of this one is the largest because everything else is, half over here. √3/4 is a little bit smaller than 1/2. pi/8 is even smaller than that. So, but if you notice, all of the work is the same. Okay. They can also give you directions. I didn't realize that there are more on here, where the cross sections can be written in different ways. And this is another reason why understanding what the directions are saying is helpful. So as we look at this, we have cross sections of rectangles whose height is twice the length of the base. Well, if the base is f of x minus g of x, and the height is double that, I know this picture doesn't look right because he didn't draw it to scale, but then you can come up with an area formula and then come up with the correct answer. And here's another one. Cross sections of rectangles whose height, whoops, I don't know what I just did there. Get that out of the way. Is 1/3 the length of the base. It follows from the same directions. And type it into your calculator. The main thing is understanding how to do this. I'm going to keep this video kind of short. Just one video. Let you work through this problem. But now you should be ready to answer questions where, perpendicular to the x-axis is a square. And then see how to set up the problem. Hit pause to write down. You try it on your own and then get your answer down. And hit pause, see if you understand it. Write down any questions you may have, bring them to class. I'd like to answer them. And then I think you're ready for your homework. Yep, you should be ready for your homework now.